All right, so looking at do now, it kind of goes off what we did the other day. So we want to get the exact same base. 3 to 3x equals 3 squared. 3x equals 2, x equals 2/3. All right, so just doing some review here. All right, so 16, I got 2 to the 4th to 4x minus 1. All right, 1/2, right? I got the 2. How do I bring it up? 2 to the negative 1 to 2x plus 1. So that would be negative 2x minus 1 equals 16x minus 4. 3 equals 18x. X equals 1/6. All right, so that's review. So now getting into the newer stuff, and we're looking at logarithms. All right, so today we're going to use another way to go about solving the above equations. So we don't have to necessarily use logs for the above equations, but we could. Right? We're looking at logs. And what we have to understand is that logs are just a different form of exponents. Now, if I have b raised to the y equals x, that's log base b of x equals y. Right? That's consistent. In this situation, some rules we have. The x, which is the argument, that has to be greater than 0. Right? It has to be positive. B, which is the base. B has to be greater than 0, also has to be positive, but it also cannot equal 1. The argument can be 1. And y is like, the whole thing. It's the actual log itself. One thing that helps me is I think about this I think about it as like a wheel idea, this converting idea. This may not help you, it may help. But if I have log base 2 of 8 equals 3. Right, if I want to convert from log form to exponent form, I think about this wheel. And the line up top is always equals. 2 to the 3rd equals 8. And if I'm going back, 2 goes under 8 and equals 3. Some people like this, some people don't. I'm just giving you a different idea to kind of think about it. Another option about remembering how to convert, if you just know something, if you just know that log base 2 of 8 equals 3 and 2 to the 3rd equals 8, you can always go back to that and relate to it. So, just the converting idea. So if I use that wheel idea, log base 3 of 243 equals 5. 2 to the 6 equals 64. 6 goes under 36 and equals 2. 729 to the 1/3 equals 9. Man, we got a lot going on here, but whatever. So log of 27 over 125 of 5/3 equals negative 1/3. Right, all those using that wheel concept, converting. All right, so our basic log problems, super basic log problems. We could have a log and we could solve for the argument, the exponent, or the base, whatever it is. And all we have at the moment is just, hey, we have a log, make it into an exponent. Right, so we are solving for x. Now, some people like it better if it's over here. That's fine. So we get, if we convert, 2 to the negative 3 equals x. So that tells me 1 over 2 to the 3rd equals x. So x equals 1/8. So this is true every single time. If you're solving for the argument, all we do here is convert and solve. That's going to be consistent every single time. So if we make this equals y, not have that back there, right? If we're solving for that answer, that exponent, if I convert, 2 to the y equals 1 over 8. Right, so it's not as easy as the top problem. Right, so I can do a change of base. So if we are solving for that y, right, if the variable's in that spot right there, it will always be a change of base problem. 2 to the y equals 2 to the negative 3, y equals negative 3, every single time. Right? If we're solving for the base, right, we're solving for our base down there. So we got x to negative 3 equals 1 over 8. Right? Reciprocal power. If I use my reciprocal power, I can solve. Right? So every time we solve for the base, we use a reciprocal power to solve. Right? So this gives me x. All right, it's a negative exponent, so I flip it, 8 to the 1/3, so x equals 2. Right, these are consistent. Solving for the argument, convert and solve. Solving for that answer, change of base. Solving for the base, reciprocal power problem. That will hold true every single time. All right, so if we do these, all right, I'm solving for the argument, convert and solve. All right, solving for that answer, change of base problem. All right, solving for the base, x to the 2/3 equals 4. Use the reciprocal power. All right, so remembering with the reciprocal power, that is the square root of 4 to the 3rd power. So 2 to the 3rd equals 8. Now, what about if we have ln? Right, so I always hear like, oh, it's different, it's different. It is the most undifferent thing ever. So understand, ln is a log base e. They are logs. Right? ln is a log, it's a base of e. You know, it's called a natural log on your calculator, it's ln, but it is a log base e. So this first problem really is log base e of x equals 4. Right, so if we're solving for that argument, as we have in the previous rules, we just convert and solve. E to the 4th equals x. Now on our calculator, if we hit second ln, it brings up e. If we raise it to the 4th power, we get our answer. So don't think that ln is this big, drastic, different thing. Right? It's similar, it's same exact rules as a normal log. All right, so I got log base e of e squared equals y. I convert. E to the y equals e squared, y equals 2. Log base e of e to the x equals 6. E to the 6 equals e to the x equals 6. Nothing drastically different, all relatively the same idea. All right, so those are just the normal log things. I want to get some log rules out there, and these special cases will be beneficial to us as we move forward. So if we have a scenario where the base and the base are the same thing, the answer is the argument. So if you have log base 2 of 2, technically there's an invisible 1 exponent there, so this equals 1. If you have log base 2 of 4, that's log base 2 of 2 squared, so it's 2. Log base 2 of 8, that's log base 2 of 2 to the 3rd, so it equals 3. Having these shortcut methods will make things a lot easier for us. All right, so anytime you have the exact same thing, if you have log base 10 of 100, that's log base 10 of 10 squared, it equals 2. Right? Taking the things out of log will make things easier for us. Right? If they have the same base, just like, you know, kind of similar to what we have here, but there's always going to be a 1. This is 1. So every time, log base 6 of 6 equals 1. Log base 19 of 19 equals 1. Log base 20 of 20 equals 1. If the argument is 1, it will always be 0. Log base 4 of 1 equals 0. And why is that? If we convert 4 to the 0 power equals 1, everything raised to the 0 power equals 1. If the argument is 0, there is no answer. All right, so if we have log base 4 of 0 equals x, 4 to the x equals 0, what could x be? Nothing. There's nothing that's going to work there. And the last one, in this situation, Right, a little bit different. We have an exponent, and in this case, the exponent is a log. If these are the exact same number, it equals x. So if we have like 8 log base 8 of 2 equals x. Right, understanding this whole thing is the exponent. So if I do my convert idea, this goes under that and equals that. Log base 8 of x equals log base 8 of 2. Since they both have the exact same log, that means that we could just solve the arguments and x is 2. Right, so we'll keep going on these rules, but I just wanted to get them all out there for you. Right, so here's some of our log rules. And when in doubt, you can always set equal to x and solve. Right, I'm not going to really promote that. Right? This is if needed. I like just kind of knowing the rules. So like this first one, this is 2. There's nothing to be done. Now the second one, right, I could write this as 5 to the third. So the whole thing is 3. But if I go with this equals x idea, if you're stuck, you can convert 5 to the x equals 125, 5 to the x equals 5 to the third, and that's how we get x equals 3. So I'm hoping you know like the idea in the red, but if you have to, set equal to x to convert. All right, shortcut rules, same base, 1. All right, so if I'm not feeling this one, I got 36 to the x equals 6, 6 to the 2x equals 6 to the first, 2x equals 1, x equals a half. And think, the question is, 36 to what power is 6? 1/2. Argument is 1, 0. These two numbers are the same, 16. Oh, argument 0, no solution. All right, let's see this one. 1 to the x equals 9. Nothing. Nothing's going to work. Why? One of our rules, the base has to be greater than 0, and the base can't equal 1. Right, if I'm unsure, set it equal to x. 2 to the x equals 1 over 8. 2 to the x equals 2 to the negative 3. X equals negative 3. Or at this moment, just no. Okay, so I got 2. So this would be 2 to the negative 3. Done. Right, 10's got a lot going on. So I'm going to make it 25 over 36 to the x equals 216 over 125. All right, so 25 and 36, I got 5 squared and 6 squared. So I got 5 over 6 to the 2x. Now, 216, we're talking about 6 to the third over 5 to the third. But I need to have it as both as 5 over 6 or both as 6 over 5. So if I flip it, I can make it negative 3. 2x equals negative 3. X equals negative 3 over 2. All right, what do we got here? In this situation, since they are the same, this whole left side is just 12 minus x. Right, so I'd have x equals 3. So the rule is, if the base and the base of the exponent are the same, it equals the argument. And if we're stuck, right, we could convert. So if I were to convert this, do the wheel idea, that equals that, log base 5 of 9 equals log base 5 of 12 minus x. They both have the exact same log, so set the arguments equal to each other. They're all good options. Last one, review problem. All right, so I can multiply this over. I don't have to deal with that there. So I got 3 to the half x plus 1 equals 3 to the negative x squared times 3 to the 3x. Half x plus 1 equals negative x squared plus 3x. So I multiply everything by 2 to clear out the fraction. I would have x plus 2 equals negative 2x squared plus 6x. I move things over. 0 equals 2x squared minus 5x plus 2. We'll do a little guess and check here. Minus 1, x equals a half, x equals 1. Oh, no, disagree. Minus 2. It wouldn't rushed ahead, it wouldn't foil back. That one's a little bit complicated with the factoring aspect, but the idea of setting up from here to here is important, right? And usually we wouldn't have to multiply.